All right, buckle up, everyone, because today we're diving deep, deep, deep into the world of antimatter. We're talking about the lecture that blew everyone's minds, Paul Dirac, back in 1933.
Yeah, this wasn't just any lecture. This is where the idea of antimatter, something we're still grappling with today, all started.
Seriously, this is some seriously mind-bending stuff, so whether you're a particle physics pro or just along for the ride, get ready.
So set the stage for us. What was the physics scene like when Dirac stepped up to give this legendary lecture?
Well, back then, physicists were like explorers charting a whole new world. They were discovering new particles all the time, trying to figure out what the universe was made of or the fundamental building
It was
blocks.
like the Wild West out there, but with like electrons and protons instead of cowboys and saloons, right?
Exactly. And into this scene walks Dirac, and he's not afraid to shake things up a bit.
So how do you kick things off? Where do you even begin with this whole antimatter business? Well, he starts kind of deceptively, simply actually, by talking about, the basics. Matter, he says, is made of particles.
Okay, so far so good.
Some are simple, some are complex, but, and here's where things start to get really interesting, he starts talking about how these particles can be created and, get this, destroyed.
Hold on, destroyed, like gone, poof, vanished into thin air.
You got it. He's basically saying the universe isn't static. It's this dynamic, almost chaotic system where particles can just pop in and out of existence.
Whoa. Okay, I'm starting to see why this lecture caused such a stir. That's a pretty radical concept for its time.
Oh, absolutely. I mean, this idea was revolutionary. It completely changed how we view the universe. And it's this idea that leads Dirac to focus on electrons and positrons, these, seemingly simple particles.
So why electrons and positrons? What was it about them that caught Dirac's attention? Were they just like the cool kids on the block back then?
They were, in a way, yeah. I mean, they were simple enough to model, theoretically, which is what any physicist loves, but complex enough to maybe hold the key to some really big fundamental truths about the universe.
Okay, I'm intrigued.
Plus, and this is a big plus, they presented this unique challenge, right? Because to truly understand them, you had to find a way to bring together quantum mechanics, which governs the really, really tiny world of these particles, with Einstein's theory of relativity, which, as we know, explains the super fast world of stuff zipping around at the speed of light.
Okay, so I'm seeing the pieces of the puzzle starting to come together here, right?
Yeah.
We've got these electrons, they're tiny, but they can move incredibly fast.
Yeah, they're speed demons, these electrons.
And Dirac, he's like, okay, to truly understand these speed demon particles, I've got to find a way to make quantum mechanics and relativity, which normally don't really play well together, I've got to get them to at least sit at the same table and have a conversation.
That's a great way to put it, and that's where things get really, really interesting.
This is where the famous, or maybe infamous, Dirac equation comes in, right? The one that's supposed to be like the holy grail of electron understanding, but also makes your brain melt if you look at it too long.
Yeah, it's not exactly something you'd scribble on a napkin to explain, that's for sure. But what's amazing is that it actually did what Dirac hoped. It gave us incredible, and I mean incredible, insights into how electrons actually behave.
Okay, so what kind of insights did, like, tell us their favorite color or something? What does it even mean for an equation to explain how an electron behaves?
Well, for one, it explained this thing called electron spin.
Electrons spin.
Yeah.
Like they're out there doing pirouettes in the quantum world.
Kinda, but not really. See, before Dirac, physicists knew that electrons acted as if they were spinning. They observed it in experiments, but no one could figure out why, like what caused it.
It was one of those, it just does that okay
Hmm.
kind of things in physics.
Exactly. But the Dirac equation, it actually explained it. It showed that this spin wasn't like a planet spinning on its axis, but this fundamental property of the electron itself baked into its very existence.
Okay, so it's more like saying electrons just have this inherent spinness to them.
You got it. And this was huge because it showed that the equation wasn't just some abstract mathematical exercise. It was reflecting reality.
So that's one mind-blowing insight. Was there more? Because I feel like we're just getting started here.
Oh, there's more. This is where things get really weird. See, the equation, it also allowed for electrons to exist in states with negative energy.
Negative energy. Okay, now you're just messing with me. How can something have negative energy? That's like saying you can have less than 0 cookies.
Yeah, it's a head scratcher for sure. It's one of those things that's really hard to wrap your head around.
So how do we even begin to make sense of negative energy?
Well, think of it like this. Imagine a swimming pool that's completely full of water. Completely full, No room for even another drop.
Okay, I'm picturing it. A very full pool. Go on.
Now imagine you could somehow scoop out a bit of that water, even though it's already full.
All right, I'm trying, but I think my brain just glitched.
What you'd have is a hole where the water should be, right? That's kind of like what Dirac was suggesting with these negative energy states. They're like holes in space that are somehow emptier than empty space itself.
Okay, so we're not talking about your average run-of-the-mill emptiness here. This is like next level emptiness.
Exactly. And, at first, a lot of physicists, even really smart ones, they just thought this whole negative energy thing was, just a quirk of the math.
Like, oh, the equation spit out something weird, but we could ignore that, right?
Exactly. But Dirac, he wasn't so quick to dismiss it. He thought there had to be something more to it. And this is where things get really, really interesting.
I'm on the edge of my seat here. Tell me more.
So Dirac, he brings in this other big idea from physics, this rule called the Pauli exclusion principle.
Okay, I'm going to need a little help here. Refresh my memory. What's the Pauli exclusion principle again?
It basically says that you can't have two identical fermions, which are a type of particle like electrons, in the same quantum state at the same time.
So no two electrons can be in the exact same state at the exact same time. They're like,
Yeah.
no, this is my quantum state, get your own.
Exactly. It's all about personal space in the quantum world.
Got it. No quantum mosh pits allowed. But how does this help explain the whole negative energy thing?
Well, this is where Dirac's genius really shines through. He imagined that all those negative energy states that his equation allowed for, they weren't actually empty.
Wait, what? But I thought they were like holes.
They are, but Dirac said they were holes that were already filled with electrons, like an entire invisible sea of electrons filling up all those negative energy states.
So even when we think there's nothing there, Dirac is saying there's actually a whole bunch of something.
Exactly. And because of the Pauli exclusion principle, no other electrons are allowed into this sea because all the spots are taken.
Okay, so if this sea of electrons is already full, then where does that leave us? Where do regular electrons, the ones we observe, even fit into all of this?
That's the million-dollar question. And this is where Dirac's thinking takes an even wilder turn. He realized that if you could somehow create a hole in this sea of negative energy electrons, in other words, if you could remove one of those negative energy electrons, that hole would act like a particle with positive energy.
Wait, so the absence of something negative would look like something positive? That's kind of blowing my mind right now.
It's true. And not just positive energy, but also the opposite charge of an electron.
So you're saying that a hole in this sea of negative electrons, this absence of something, would act like a real particle with positive energy and a positive charge.
Exactly. And Dirac, he had a name for this hole, this particle with positive energy and a positive charge. He called it the positron.
And just like that, the idea of antimatter is born.
Pretty much. Just from an equation, the Pauli exclusion principle, and a whole lot of imagination.
It's incredible. But of course, predicting something and actually finding it are two different things, right? So did Dirac's crazy idea pan out? Did we ever find these positrons? So we've got this absolutely mind-boggling concept of a sea of electrons with holes in it, and those holes, they act like positively charged particles, which we now call antimatter.
Yeah, it's a lot to take in.
It really is. But Dirac's theory, it didn't just stop at predicting the existence of antimatter, did it? I mean, we've got all this talk about annihilation and creation, and honestly, it all sounds a bit like something out of Star Trek.
Well, you're not wrong to think it's some seriously futuristic stuff. And yeah, Dirac's theory went even further. He proposed that when an electron, a regular electron meets its antimatter twin, a positron, something incredible happens.
I'm a guess. They have a little quantum tea party and then go their separate ways.
Not quite. They actually annihilate each other.
Annihilate. Like gone, kaboom.
Gone, and all their mass, it gets converted into pure energy. Poof.
So they just disappear in a burst of energy. What happens to all that energy? Does it just, like, vanish too?
It's not vanishing, more like transforming. The energy that was all bundled up in the mass of that electron and positron, it gets released, but in a different form, like maybe light or heat.
Okay, so it's like a cosmic game of energy exchange. Matter turns into energy, energy maybe turns back into matter. It's wild. But this is physics we're talking about, right? Not just some cool ideas. It's got to be testable. So did Dirac's predictions about antimatter, about this annihilation thing, did they actually hold up in the real world?
That's the really amazing part. As crazy as all this sounded back then, experiments actually confirmed it.
No way. Seriously?
Seriously, they actually discovered the positron, the electron's antiparticle, just a year after Dirac gave that lecture back in 1932. And since then, we've seen this annihilation thing happen again and again in experiments.
That's incredible. So Dirac essentially predicted a whole new kind of matter and a whole new way for matter and energy to interact just by looking at an equation.
Yeah.
That's amazing. But he didn't stop there, did he?
No, Dirac was on a roll. He took this whole antimatter idea and ran with it, speculating about, get this, stars made completely of antimatter.
Antimatter stars. Like the entire star is just antimatter. That's insane.
That's Dirac for you. He figured, hey, if the universe is really as symmetrical as his equations suggested, then there should be antimatter stars, maybe even entire galaxies made of the stuff.
So you're telling me there could be entire galaxies out there made of antimatter that we just haven't seen. That's both mind-blowing and also a little terrifying, right? I mean, what if an antimatter galaxy bumped into a regular matter galaxy?
Let's just say it would be a very bad day for both galaxies.
That's an understatement. But seriously, the idea that something as fundamental as antimatter was just waiting to be discovered, hidden in the math, in the equations, it just shows you how much we still don't know about the universe.
Totally. Dirac's work really makes you realize that what we can observe, what we can see and touch, it might just be a tiny fraction of what's really out there.
It's enough to make your head spin, that's for sure. And it leaves me with so many questions. Like, are there antimatter stars and galaxies out there? Could there be other universes made entirely of antimatter? And what other mind-blowing secrets are still hidden in the equations, just waiting for someone like Dirac to come along and unlock them? Well, that's all the time we have for today's deep dive. From electrons to positrons, from annihilation to the possibility of antimatter galaxies, we've journeyed to the very edge of physics and glimpsed the incredible possibilities that lie beyond. Join us next time as we delve into another fascinating chapter in the story of science.